Before describing what's in the course, let me tell you what is not in the course. What is not here is the set of techniques to design code for any kind of channel. I try to focus rather on the principles that are underlying the design of codes and the techniques for computing their performance and the techniques for decoding codes. And I will specifically focus on codes designed on the signal space. So if we know something about algebraic coding and decoding, that's fine, but it would not be needed. I will not cover any algebraic coding and decoding at all. I will rather focus on maximum likelihood decoding or maximum a posteriori decoding, or in a simpler word, it's soft decoding of codes. This is the sorry, but I made a mistake here. Okay, this is the outline of the course. I first review some of the basic concepts about coding in the signal space, reviewing the definition of signal-to-noise ratio, the definition of error probability, and its calculation. Then I will focus on fading channels, how to model a fading channel and what are the effects of fading channels, in particular flat fading channels, on the performance of a code. And then I'll describe two techniques for analyzing code. One is by defining code of a trellis, a kind of generalization of what you probably know about a trellis describing convolutional code. So we'll see essentially that all code can be represented through trellises. And then I will spend a considerable amount of time in describing codes of a vector graph, and in particular techniques that allow you to decode a code defined on the vector graph, specifically iterative decoding techniques, so-called turbo decoding techniques. And based on a vector graph representation, I will describe briefly turbo code and low-density pair-check code and the techniques that allow you to decode this kind of code in a iterative way. And finally, I'll cover space-time coding, MIMO, multiple input, multiple output channels, and in particular space-time coding. Please interrupt me whenever you feel like, whenever you need an explanation, some additional details, or you want to correct me if I say something not fully correct. Okay, let me start with coding in the signal space with some basic definition. I assume that all of you are familiar with all these definitions, but I want to focus on some specific variation on the theme of definition of bandwidth and signal-to-noise ratio that might be useful. Let me first define what is a finite signal constellation. We are talking about coding in the signal space, so we are not considering, or we are considered that only marginally, considering codes whose as vectors whose elements are abstract symbols. Now we are considering code as vectors whose elements are waveforms, and this is a code in the signal space. So let me define a finite signal constellation. A signal constellation is just in this context can be viewed as a set of I call it S, a set of vectors in the Euclidean n-dimensional space. Most cases n, capital N is equal to 2, so we are considering signals in the two-dimensional space, like PSK or QAM or any two-dimensional constellation. And we call these vectors points or signals, according to which we are considering a geometric representation in Euclidean n-dimensional space, or we are considering waveforms. And we use these constellations, this constellation for transmission over a noisy channel. For the moment, I won't specify what kind of channel we'll consider, because we're going to consider both additive wide Gaussian noise channel, but in particular, we are considering a flat fading channel. The energy in this context, the energy of a signal is the square norm of it, or the sum of the magnitude squared of the components of the vector. Okay, now a few definitions. The number of elements of the signal space will be denoted by capital M. That's the number of signals that we have available. And consequently, the maximum amount of information that can be carried by the constellation S is logarithm of base 2 logarithm of the number of elements in the constellation. It's typical to assume, although it's not necessary, but it's typical to assume that the number of signals in the constellation is the power of 2, and consequently capital M can be written in the form of 2 power small m. Now, mapping or modulation. In this context, what do we mean by a modulation? Well, we define a one-to-one correspondence that's called a labeling or a mapping that associates with each element of the constellation an m tuple of binary digit. Remember that m is the number of, well, it's the exponent of this. So capital M is the number of points in the constellation. Small m is defined like this, a logarithm of m. And this is the number of bits that can be, a binary digit that can be associated with each element of the constellation. This is called a labeling or a mapping. And this labeling of mapping may play some role in the design of the system and also in the performance of the system. We'll see a couple of examples of this. So we call the association of this m tuple of binary digit with the signal modulation. Okay, so in the abstract way, we define modulation as the association of an m tuple of binary digit with an element of the constellation. The choice of labeling is not neutral. I mean, different labelings may imply different performances. For example, for a bit interleaved coded modulation, we'll see an example. And for the evaluation of bit error probability, there's another example that we are going to discuss briefly. So the demodulator task is to transform what is observed at the output of the channel back into the sequence of binary digits that are delivered by the user. So that's pretty standard stuff, except for a few definitions that may not be the same as you are familiar with. As I said before, the maximum amount of information that can be transmitted by using a certain constellation is measured by the number of bits per signal, the logarithm of capital M. Now, every signal, remember, has capital N dimensions, and consequently we can define a transmission rate. There are several ways of defining a transmission rate, but it's especially convenient in this context to define the transmission rate in bits per dimension. And now I'm going also to use this bit per dimension definition of transmission rate when I define capacity, which in my opinion clarifies a few things. So bit per dimension is rho. It's the logarithm of capital M, the number of signals in the constellation, divided by the number of dimensions. So this is a crucial quantity, the bit per dimension. Okay? Now let's consider the time. Okay? In many cases, in particular systems, we are interested in bits per second, how many bits per second we can transmit. Now, assume that we transmit the signal that has n dimensions every capital T second. Or in other words, we have the number of signal transmitted every second is t minus 1. T is raised to power minus 1. Okay, so we transmit at the rate n over t dimensions per second. N is the number of dimensions per signal. T is the number of second per signal, and consequently the rate in terms of bit per second is given by this expression. So we have logarithm of 2 divided by m, that's the bit per dimension, multiplied by dimension per second, n over t. So we have number of bits per second, that's logarithm of m divided by t. Okay, so second definition. So first, let me recall this. Bits per dimension, log m divided by n. Bit per second, log m divided by t. Now let's introduce concept of bandwidth. We need for our transmission, we need a certain bandwidth, okay? And how we define bandwidth is rather crucial in our calculation. There are several ways of defining bandwidth. But anyway, let's for the moment focus on the fact that we assume that the bandwidth needed to transmit the signal that we have selected is beta hertz per dimension per second. So the bandwidth requirement will be beta multiplied by the number of dimensions divided by the number of seconds. So the bandwidth requirement will be beta times n divided by t. Often it is assumed for simplicity that beta is equal to 1/2, but it's not the only definition, simply because there are several possible definitions of bandwidth. The bandwidth that contains 99.9% of the power, or the 3 dB bandwidth, or root mean square bandwidth. There are several definitions. In this course, I will focus on one specific definition of bandwidth that is very useful, it's very convenient, and it comes from the so-called 2WT theorem that says that the approximate, well, asymptotically, the dimensionality of a set of signals whose duration is capital T and whose bandwidth is W is n equal to 2WT. Okay, that's the 2WT theorem, very important. If we can use this, which is an approximate or asymptotic equality, as an exact equality to connect together the dimensionality, the bandwidth, and the duration. And this leads to the definition, very convenient definition of Shannon bandwidth. I'm indebted to Jim Massey for this definition. I find it very extremely useful. The definition of Shannon bandwidth is the following. The Shannon bandwidth of a signal set with n dimension is n divided by 2t. So if the duration of the signal is t and the dimension is n, we call Shannon bandwidth the ratio between n over 2t. And this comes from the 2WT theorem, the fact that asymptotic, approximately in general, n is equal to 2WT. If we take this as an equality and if we use it to define W, we end up with the definition of Shannon bandwidth. Okay? And this, well, there are a few other details that are interesting about the definition of Shannon bandwidth. For example, the way Jim Massey defines the spread spectrum is a signaling technique such that the bandwidth used is much larger than the Shannon bandwidth, which is not an obvious definition. That depends on the fact that the Shannon bandwidth essentially can be viewed as the minimum bandwidth necessary to transmit signals. The bandwidth can be expressed in hertz, but in many cases it's appropriate to define bandwidth in dimension pairs per second. Actually, you see that W is n over 2t, so this is number of dimensions, this is second, so we can also define the Shannon bandwidth in terms of dimension pairs per second. Why dimension pairs rather than dimension? It's convenient because in most practical application of coding and modulation, our signals are two-dimensional, and consequently we are using signals that have one-dimension pair. Somebody prefers calling these complex dimensions. So the one-dimension pair is equivalent to a complex dimension, but I prefer calling them dimension pair. And you see here that we have n over 2, and it's a natural way of defining dimension pairs. Again, the Shannon bandwidth tells you what's the minimum amount that the signal needs. Whatever Fourier bandwidth definition you use will be the actual amount that the signal uses. Okay? So, for example, if we have an MRE PAM, that's one-dimensional system. So the Shannon bandwidth is W equal to N, that's 1 over 2T. So MRE PSK has two dimensions, and consequently the bandwidth is 1 over T. So you see that the whole thing is simplified. But this is a kind of abstract definition of bandwidth, so it's not the actual bandwidth that used. That's the minimum bandwidth that is needed. But the definition, all the calculations, the definition are much easier if we assume that the bandwidth we are dealing with is Shannon bandwidth. So the information rate of the source, we are going to define the signal-to-noise ratio. So the information rate of the source that we call RB is bit per second, and it's related to the number of waveforms used by the modulator, that is M, to the duration of the waveform, T, and so we return to the previous definition that bit per second is given by log M divided by T. Now, what is the average power expended by the modulator? The power is equal to the energy. Remember that we had defined the energy in terms of the norm of this vector divided by T. Right? So that's the power. The energy is the average energy of the modulator signal, so we have to take the sum of the energy of each signal and divide by the number of the signals. That's simple. Each signal carries log M information bits, so we can define the average energy expended by the modulator to transmit one bit, and this is the relation we need. The energy is equal to the energy per bit multiplied by the number of bits per signal. And consequently, the power will be equal to EB multiplied by log 2 of M, which is E divided by T, so we can write it in the form EB times RB. That's a pretty standard formula, but a very important one in our calculations. Now, define the signal-to-noise ratio. Signal-to-noise ratio is the ratio between the average signal power and the average noise power. Assuming additive white Gaussian noise with power spectral density equal to N0 over 2, we multiply N0 over 2 times twice the Shannon bandwidth, and we have N0W. Remember, the W in our calculation is always the Shannon bandwidth. So signal-to-noise ratio will be given by let me use this, by the power divided by N0W, and we can rewrite it in the form EB over N0, energy per bit divided by power spectral density multiplied by RB over W. And this is, again, a rather standard way of doing the calculation. Remember, again, this is valid for W equal to the Shannon bandwidth in our context. RB over W is called bandwidth efficiency. Again, I owe to Jim Massey the observation that it's kind of a misnomer, because an efficiency should not exceed 100%. But this is called efficiency. It can be 2, 3, 4, 10, whatever. So should not be called bandwidth efficiency. Anyway, everybody calls it bandwidth efficiency, and I will follow suit in this case. So RB over W is the number of bits per second that we can transmit in 1 Hertz of Shannon bandwidth. And it's related to the number of bits per dimension. So RB over W is equal to 2 logarithm of M divided by the number of dimensions. So log M divided by dimension pair. So RB over W is the number of bits transmitted per dimension pair. Again, you use dimension pair instead of dimension simply because it's convenient whenever we use two-dimensional modulation. So we have a possibility of considering bit per dimension pair, which the one that I prefer, or bit per second if we are interested in considering the time dimension in the calculation. But anyway, RB over W can be written as log M divided N over 2. And it's a very convenient way of computing the bandwidth efficiency of a modulation scheme, because it just the only thing we need is the number of signals in the constellation, capital M, and the number of dimensions that are used, and then we have RB over W. But this is, again, let me repeat once more, depends on the fact that W is the Shannon bandwidth. Now, let's define what is called the asymptotic power efficiency. I've discussed the bandwidth efficiency, so how the constellation uses the bandwidth. Now let's see how efficiently the constellation uses the power, which is another resource that we have to spend whenever we design a coded modulation scheme. I shall return on this, but I assume that you are familiar with the fact that for high signal-to-noise ratio and for additive white Gaussian noise channel, we can approximate the error probability in this form. There's a constant C, I return on the significance of this constant, multiplied by the Q function. This is the Gaussian tail function, whose argument is the minimum Euclidean distance of the constellation. I shall return on this as well, divided by 2 and 0, twice the power spectral density of the noise. Now, what is the asymptotic power efficiency? We take this quantity, the argument of the function Q. We remember that the function Q is a decreasing function, so the error probability increases when the argument of the function decreases and vice versa. The asymptotic power efficiency is defined in this way. We rewrite the argument of the Q function in the form of square root of 2EB over N0, remember the energy per bit divided by power spectral density, multiplied by gamma. And gamma is the asymptotic power efficiency. So by rewriting this, we have a kind of normalized way of writing error probabilities, especially if we disregard the coefficient C, which makes sense especially for very small error probabilities or high signal-to-noise ratios. And we define the asymptotic power efficiency as the coefficient gamma that multiplies 2EB over N0. The reason why we choose this, especially we choose this factor 2, comes from the fact that we want to define a baseline constellation such that gamma is equal to 1. Okay, so the higher gamma, the higher the asymptotic power efficiency, and consequently the higher the efficiency of use of power by the constellation. So gamma is the square Euclidean distance divided by the energy per bit. So gamma tells us how efficiently we increase the distance of the constellation given a certain energy. For example, consider an antipodal constellation. An antipodal constellation is a constellation that has two signals only, with amplitude plus or minus square root of epsilon here. Okay, so the energy is equal to the energy per bit because the constellation is binary, and the minimum Euclidean distance is given by 2 square root of E. Okay. So if we plug these terms into the definition of gamma, square Euclidean distance divided by 4EB, we have that gamma is equal to 1. So this is a baseline. So gamma equal to 1 is the power efficiency, the asymptotic power efficiency of the constellation. Why asymptotic? Because the definition makes sense when the error probability is actually a form like this, Q of this. And this is valid only for significantly high signal-to-noise ratio. Otherwise, it doesn't make much sense. In fact, the asymptotic power efficiency does not make much sense in practice if we are not working for that very small error probabilities. So we can evaluate the quality of a constellation by evaluating how efficiently the constellation uses bandwidth, and this bandwidth efficiency RB over W, and power. So remember that RB over W is given in terms of M, the number of signals in the constellation and the dimensionality of them. So we have that for PAM, this is equal to 2i's logarithm of M. For this binary, for this two-dimensional constellation, PSK and QAM is the logarithm of M. And for FSK, right, orthogonal FSK is 2 logarithm of m divided by n. We observe, for example, a number of things that will be summarized in the chart. And we observe that as we increase capital M, then the bandwidth efficiency of PAM, PSK, and QAM increases, while decreases for FSK. Asymptotic power efficiency, we can compute this once we are able to evaluate error probabilities. And some relatively simple calculations that show that these are the values of gamma for PAM, PSK, QAM. You see that as m increases, gamma decreases here, while for FSK, as m increases, gamma increases as well. Okay, so we see that we have two different kind of trade-offs. For PAM, PSK, and QAM, increases the number of signals in the constellation, increases the bandwidth efficiency, but decreases the power efficiency. Vice versa for FSK, whose number of dimension increases when we increase the number of signals, because every signal occupies an additional dimension. So we have an idea of what we can get here, because you cannot have both high power efficiency and a high bandwidth efficiency. We have to choose which one we want to prevail. So this chart summarizes these things, and the ordinate show the asymptotic power efficiency gamma, and the abscissa show the bandwidth efficiency RB over Shannon bandwidth. You see what happens with that. Essentially, you see that these all these constellations are located in around a curve that looks like this. We have to choose whether we want a high power efficiency or a high bandwidth efficiency according to the specific need. If our system is bandwidth limited, then we want a high bandwidth efficiency. Our system is power limited, we need a high power efficiency. Now let's focus in particular on the additive wide Gaussian noise channel, and let's see how we can evaluate the relevant parameters, particularly error probability for transmission on additive wide Gaussian channel. Again, we assume that the digital modulator uses capital M signals, X with X belonging to a constellation. You may want to make a slight shift in the way you interpret these quantities. For the calculation, for all the example that I've shown you before, S is what we maybe call an elementary constellation. Okay? It's not necessary to consider X as an elementary constellation. We can think of X as a vector that contains elements that are elementary, signals from an elementary constellation. For example, you may think of X as a vector with small n dimensions. Each one of them is an elementary signal. Right? So we may shift our attention from elementary constellation with S two-dimensional, for example, to something more complex that is a code in the signal space. So S may include vectors that are actually code words, whose elements are 1 or 2 or whatever dimensional signals. Okay, so we may think of everything in this way. So the calculation of error probability will be at the same time involving probability of erroneous demodulation of an elementary signal or erroneous decoding of a code. Okay, there is no difference, no conceptual difference between transmitting one elementary signal or transmitting a vector whose elements are elementary signals. So suppose that the digital modulator uses capital M signals taken from a constellation. So maybe X may be an elementary signal or maybe a code word. Okay, so what we observe, the definition of additive Gaussian noise channel is the following. Y is equal to X plus N, what we have transmitted, plus a vector with the same dimensionality as X, of course, whose components are Gaussian random variables. the demodulator, or you may want to call it decoder if you prefer, decides that the transmitted x is x hat if the Euclidean distance from what we observe and x hat is the smallest. So this is the optimum decoding or demodulation rule. We minimize the distance, the Euclidean distance, this norm, between what we observe and what we have possibly transmitted by looking into all possible vectors that belong to the original constellation S. This is X hat. This is a maximum likelihood decoding or demodulation, and this minimizes the probability of an error in the reception of vector x, provided that all x's are transmitted with the same probability. That's the standard detection, standard demodulation theory. But anyway, let's focus on this minimization of Euclidean distance, because as we shall see with the fading channel, we have essentially a minor modification of this, and when we'll examine MIMO tomorrow in multiple antennas, we'll see that the maximum likelihood detection rule is essentially formally identical to this one. Now, error probability, the symbol error probability, which is the quantity that we minimize with maximum likelihood detection, minimum distance detection, provided that the x's are equally likely, is the average probability that the decision of the modulator or the decoder is wrong. That is, the modulator chooses x hat different from x when x was transmitted. That's the symbol error probability. We make the assumption, always make the assumption here, that the probability of a transmitted vector is equal to 1 over m, that is all symbols are transmitted with equal probabilities, and this is the error probability, the definition of error probability. P of E is equal to the average value, and you remember 1 over m is the probability that x is transmitted, of this quantity, the probability that the decision, x hat, is not equal to the transmitted vector when x is the transmitted vector. That's the definition. The calculation of this is generally hard. There are a few cases in which it can be computed exactly, particularly for elementary constellation, but in general it's very difficult to compute it exactly for more complex cases when x is a vector of signals, for example. So given the difficulty of computing that exactly, a number of approximations have been developed. I'm going to describe you only the simplest of these approximations, which is based on a union bound. The union bound says that the probability of error given that x was transmitted, the probability of error given that x was transmitted is exactly this quantity. Okay. The probability of error given that x was transmitted is upper bounded by this quantity. It's called the pairwise error probability. I'll comment on this in a moment, whose summation taken with respect to all x's that differ from x. This is, again, it's called pairwise error probability. Another example of a misnomer, as I will discuss in a moment. Anyway, before discussing how we define the pairwise error probability, let's just focus on this inequality based on the union bound. And if we use the union bound on the expression of error probability, the average error probability, which is this, we get this one. So 1 over m, double summation with respect to all x's, x hat differing from x, and x running through the whole constellation, pairwise error probabilities. So this is the union bound. The union bound is very convenient to compute because it's simple. And it's usually good enough for a good approximation to error probabilities when the signal-to-noise ratio is large enough, or if you prefer, when the error probability is low enough. And In addition, in many cases, exact calculation is not possible, and consequently one may use the union bound, and the union bound is accurate for high signal-to-noise ratio, so when the error probability is very small. So if you want to use simulation, for example, then for simulation it may be convenient to do something like this. First, you evaluate the union bound of error probability. So this is the signal-to-noise ratio, and this is the error probability. Then you know that this is accurate, especially for high signal-to-noise ratio. So you do your simulation and you get some points like this. And at a certain point, with your simulation, you get very close to the union bound. Consequently, you can stop doing simulation because you know for sure that the error probability will be essentially given by accurately enough approximated by the union bound. So it's good because the simulation, evaluation of an error probability by simulation is more expensive for small error probabilities. Okay, so you start with large error probabilities and you keep on doing simulation until you hit the union bound curve. So union bound can be made to good use. Of course, there are other approximations to the error probability that are better than the union bound, but usually also much more complex to evaluate. So let me focus now on this building block of calculation of error probability. There is pairwise error probability. Another example of a misnomer, it's not an error probability. The pairwise error probability is the probability that when X is transmitted, the received vector is closer to X hat than to X. Remember that the decision rule consists of finding the signal that lies closest to what we receive. Okay? So we compute, in principle at least, we compute all distances between what we have possibly transmitted and what we have received, and we pick the smallest one. It may happen that X hat is closer, Y is closer to X hat than to X, in which case the pairwise error probability is the probability of this event. But this does not mean that we choose X hat. We choose the signal that is closest to Y, while the pairwise error probability is probability that Y is closer to X hat than to X. So we choose eventually the one that is closest to X. And many of them may be just closer to Y than X is. So if we have only two signals, X and X hat, then pairwise error probability is the error probability. Because if Y is closer to X hat than to X, then in this case we do choose X hat. There are only alternative X hat and X. If Y is closer to X hat than to X, then we choose X hat. Then in this case, in the binary case, this is the error probability. Otherwise, it's not the error probability. It's simply the probability that Y is closer to X hat than to X when X was transmitted. This is why I claim that calling it pairwise error probability is a misnomer because it's not an error probability. Now let's compute the pairwise error probability. This calculation is useful because we shall see, even if you are familiar with it, it's better to review it because it will return also in the evaluation of error probability of coding for the fading channels and also for the MIMO, for multiple antenna channel. So remember the definition, pairwise error probability is the probability that X hat and Y, the distance between Y and X hat is smaller than the distance between Y and X when X was transmitted. So the first line of this chain of equality is just the definition of pairwise error probability. Now, what is y? Well, we have assumed that x is transmitted, and consequently y is x plus n. Remember that we are considering additive y Gaussian noise channel here. So we have x plus n minus x, and here x plus n minus x. Now, this can be written in the form n plus the difference between the two signals less than the norm of n square, because x and x cancel out. If we expand this norm, we get the scalar product between n and the difference of two signals greater than the magnitude square of the distance of two signals. This is the pairwise error probability. What can we do now to evaluate the pairwise error probability? Well, we observe that this scalar product between n and the signal difference is a linear transformation of a Gaussian vector x, well, because it's a scalar product, and consequently it's a linear transformation of the sorry, I wrote x here, there's a misprint, it's n, Gaussian vector n. So it's the Gaussian random variable, okay? Any linear transformation of a Gaussian random variable, Gaussian vector, say, yields a Gaussian vector. The mean is 0 because n itself has mean 0, and the variance can be easily computed and is equal to n0 over 2, variance of each component of n multiplied by the magnitude square of the norm square of x minus x hat. So this calculation, the pairwise error probability, is reduced to the calculation that a Gaussian random variable like this, whose mean is 0 and whose variance can be computed, is larger than this quantity, which is a deterministic quantity. So the calculation is easily done by observing that for a Gaussian random variable whose mean is 0 and whose variance is sigma square, we have this equality. The probability that Gaussian random variable exceeds the value x is equal to the Gaussian tail function q with argument x n over sigma. So we have computed the pairwise error probability in exact form. So this is the final result. So this is the pairwise error probability. It may be convenient, in many cases it is, and it will be specifically in the case of transmission over a fading channel, to upper bound this Q function, the Gaussian tail function. Sorry. The Gaussian tail function by an exponential. So this is upper bounded rather closely, again, especially for high values of the argument of the Q function, as the exponential of minus x hat squared divided by 4 and 0. Okay, this is a very convenient approximation. So we have two approximations here we should remember. The first one comes from the use of the union bound, and it's tighter when the signal-to-noise ratio is large. The second one, which may or may not be used, but it's very convenient to use it, you approximate the Q function, the Gaussian tail function, with an exponential. And again, the approximation is good, especially when the signal-to-noise ratio is high. And consequently, the two approximations are consistent. Okay, so we have this upper bound that can be obtained, let me summarize, can be obtained by plugging this expression of the pairwise error probability in this equation here. Okay, we compute or we approximate the pairwise error probability, and we get an upper bound to the union bound to error probability. What we have to do is to take the double summation of these terms with respect to all x hat that differ from the originally transmitted x, and with respect to all x's in the constellation. So this calculation may be painful, especially when we have a large number of signals or vectors in the constellation. In some cases, we can simplify the calculation by exploiting certain symmetries in the constellation. Observe that this exact value of pairwise error probability, or its approximation thereof, depends on the distance between x and x hat, and consequently, if we have a certain symmetry property of the constellation, in particular, if we can say that the distance between pairs of signal x and x hat as seen from any signal is the same, I mean the set of distances is the same whatever x we run, then we can remove one of the summation and end up with the expression of error probability like this. That's just a way of exploiting symmetries. There's no specific theory in it. We discovered that in this double summation, one of the summation is not necessary simply because whatever the argument of the sum, we get the same result. So if we discover that, obviously we can choose any x as the reference point and run only the x hat not equal to x in order to get the upper bound to the error probability. And this is the simplest case that can occur, but we need certain symmetries that are not necessarily satisfied. For example, for PSK, we have this symmetry. For QAM, we don't. So I show you that this is true for PSK, and it's a simple example of calculation. For PSK has this symmetry property. It's called a distance uniformity. We observe, in fact, that every signal here, this one, etc., has other two signals at the same distance, square root of 2e, where e is the energy of the constellation. And consequently, we use the upper bounds, and probability of error is equal to upper bounded by three terms. 2q square root of e over n0 plus q square root of 2e over n0. This depends on the distance between this point and the two adjacent points, the so-called nearest neighbors, and this term depends on the distance between the reference point and the other point at the largest distance here. So this is the union bound. So you see that the union bound involves only the calculation of distances. We observe that they have two types of distances. Two signals are at distance square root of 2e. One signal is at distance 2 square root of e, and consequently we sum up three terms. This is just doubled, three terms that give us the pairwise error probability and consequently the probability. Then we can express everything as usual in terms of EB over n0, energy per bit over n0. We observe that each signal carries 2 bits. There are 4 signals, and consequently logarithm of 4 is 2 bits per signal, and consequently can express the error probability in this form. So this should be well known, I believe. Now let's see what happens asymptotically. Let me return to an expression that I mentioned before. Before I mentioned that the error probability asymptotic for high signal-to-noise ratio can always be written in the form of constant multiplied by q square root of gamma 2 EB over n0, okay, in this form. Let's see that this is actually true. We have, in general, the union bound to error probability given by this expression. Okay, this is the definition of error probability, and this comes from the union bound that we can write in terms of the pairwise error probability. Now, what happens when n0 becomes vanishingly small? Well, then the right-hand side, since this error probability, these pairwise error probability are Q function, and the Q function are a steeply decreasing function, it happens that all the terms is dominated by the term that corresponds to the minimum argument of the Q function. Remember, Q function is a decreasing function. So it's dominated by the pairs of signals that have the minimum distance. So we can write that P is approximately upper bounded, approximately because we are removing terms here. This is an exact upper bound, but we are removing terms here, so it may not, what remains may not be an upper bound anymore. A constant alpha, which is the number of terms that involve the minimum distance here, times the probability of the pairwise error probability when x and x hat have the minimum Euclidean distance. So when this is the minimum value across a constellation. So we see that this is equal to a constant multiplied by q of the Euclidean distance divided by square root of 2 and 0 that we want to write in this form if we define this quantity, the asymptotic power efficiency. Okay, so this actually shows that that approximation was correct. Again, this is a more an approximation than a bound. It's an approximate upper bound. Let me repeat this because this is a true upper bound, but we are removing terms here, all terms that do not involve the minimum distance between these two signals. Consequently, this is an approximate upper bound, although it's a good approximation, especially when the signal-to-noise ratio is large enough. What is the bit error probability? The quantity that I've been considering so far is the probability of error in a vector x. So it may involve a full vector of waveforms. Actually, one may observe that what we are transmitting is a set of bits that carry the information that we want to convey from the transmitter to the receiver. So we may be interested, and in many cases we are interested more in the bit error probability. The probability that a bit conveyed through the channel is received erroneously by the receiver. We can get the bit error probability is even harder to compute exactly than is the word error probability or the vector error probability, and consequently it's convenient to bound PB of E, but we have a simple and convenient and tight enough bound on bit error probability that it can be obtained by simply observing what follows. Every signal carries log m bits. Okay? That's the label of the constellation in our terminology. Consequently, when we have an error on a symbol or in a vector, how many bits are in error? But at least one, and at most log m. At least one of them is there, because if there's no bit is in error, we don't have an error on the whole vector. The minimum number then is 1, and the maximum number occurs when all bits are in error. And consequently, we can write that the bit error probabilities is upper and lower bounded by this expression, PE over log m on the one side, and PE, probability of error in a vector, on the other side. Well, we would like the bit error probability to be as close as possible to to this term, to the smallest, the smaller between the two, PE over log m. So we would like to make it possible that whenever we have an error in the full vector, we have only a single error in the bit. That's the best possible situation. And we tried when. Since the association, the mapping of bits to waveforms is left to the designer, then the designer may want to choose the mapping in order to approach as closely as possible this bound, to have the minimum possible bit error probability for a given word error probability. And this can be done, at least for the additive wide Gaussian noise channel, by using the so-called gray mapping that consists of associating bits to waveform so that nearest neighbors differ by only one bit in their label. Why is that? Well, because we assume that whenever an error is made, provided that the signal-to-noise ratio is reasonably large, whenever an error is made in favor of waveforms that are close to the transmitted waveform. So it's very unlikely, I mean, if the signal-to-noise ratio is large, it's very unlikely that when an error is made, this signal is transformed into this signal, right? Because this is further than the two closest signals. So if we trust the channel, if the channel is good enough, then an error will be made by shifting the received signal to closer to nearest neighbors. Okay? So we, in this condition, it's convenient to have nearest neighbors that differ from the original signal by just 1 bit. So you see that nearest neighbor differ by only 1 bit. It's also possible to do it in other types of constellation. This is a 16 QAM, and you can easily verify that nearest neighbors differ in only 1 bit. This is called gray mapping. Now, what can we achieve? I mean, okay, we can compute the error probability, we can do, but what can we expect to achieve? What kind of parameters we should use to evaluate the quality of a constellation? Okay, we can say, okay, this is the error probability. Is it good or is it bad? Well, we can define a few parameters that are essentially coding gain capacity, and that I'm going to tell you about briefly. One is the coding gain. What is the coding gain? Let's plot the error probability, or the bit error probability as you prefer, in the case where we transmit a uncoded constellation that is an elementary constellation, for example 2 PSK, 4 PSK, etc. Or when we transmit a vector of these signals. We transmit a code in the signal space. Okay, if we compare the two error probabilities, we may discover that with a elementary constellation, that's the uncoded situation, we get the curve represented in blue in this picture. Then we may discover that with the coded constellation, the error probability goes like this. For small values of signal-to-noise ratio, the probability of error is larger. For high values of signal-to-noise ratio, the probability of error is smaller. And this is the situation that we are actually looking for. Okay, we call coding gain for a given error probability the difference in dB between the signal-to-noise ratios necessary to achieve that error probability in the uncoded and coded case. Notice two things. First, the coding gain has to be defined for a given value of error probability. Okay, because you see that the coding gain changes according to the value of error probability. Second thing that we consider is that in most cases we have a value of error probability, I mean a value of coding gain that may be negative in dB. In other words, coding in some cases may not be beneficial, and it may not be beneficial because the signal-to-noise ratio is so low that the coding will decrease the performance of our system. So there is a crossover point here, a crossover point that said for signal-to-noise ratios lower than this value, there is no point in doing coding. Actually, one simple sentence that summarizes this is that coding can make a good channel better, but if the channel is very bad, you cannot hope to improve it by using coding. If the channel is so bad, then coding cannot buy that much. If the channel is reasonably good, then you can improve its quality by coding. Otherwise, you may end up making things worse if the signal-to-noise ratio is not large enough. But anyway, this is the definition of coding gain. Coding gain for a given error probability is the difference in dB between EB over N0 that you need for uncoded case and for coded case. What's the limit in performance? Remember the definition of code rate in terms of bit per dimension, the logarithm of the number of signals divided by the number of dimensions, bit per dimension. This is Shannon's result, basically. This is the performance in terms of bit error rate for a binary encoded antipodal modulation. In our terminology is the elementary constellation that consists of 2 points, square root of energy and minus square root of energy. And this is the performance that we get. If we use a code, in other words, if you use a constellation whose elements are vectors, and the constellation has n dimensions and capital M vectors in it, then the best we can achieve, given the rate, is the curve is given by the curves like this. So, for example, if we take rate 1, if we want to transmit 1 bit per dimension, then this is the maximum coding gain that we can achieve for that error probability for binary with respect to binary encoded antipodal modulation. Rho equal to 0 correspond to a case in which we have a vanishingly small rate, that is, we increase the dimensionality to infinity, to close to infinity, and you see that there is this information theoretical limit of minus 1.6 dB, below which there is no reliable transmission is possible. This is the smallest possible rate that you can use, the smallest possible efficiency in terms of bit per dimension that you can use. So if we want a vanishingly small error probability, you cannot transmit with an EB over N0 lower than minus 1.6. Notice that this minus 1.6 comes at small error probability, because if you are interested in an error probability at 10 to the minus 2, then you can actually transmit at minus 2 dB. Okay, but this depends. I mean, this result, I want to focus on this particularly. This result, this famous number, minus 1.6 dB, is valid for a vanishingly small number of bit per dimension. Let me see what I can add. Okay, another couple of slides before taking the break. Another parameter, very widely used parameter to evaluate the quality of a channel, and consequently to compare what we get out of our coding system with respect to what we could potentially get if we were good enough to design a perfect system, is the channel capacity. This is a very famous formula. Channel capacity can be written in the form expressed by the first line, 1 over 2 logarithm of 1 plus SNR. I prefer measuring this in bit per dimension. We can also express it in bit per dimension pair, and we just multiply that by 2, and that's logarithm of 1 plus SNR. So if we are considering two-dimensional constellations, that the second line is the formula that we should use. If we are considering one-dimensional constellation, a bit per dimension is better. But anyway, this explain given capacity in terms per bit per dimension, it's, in my opinion, clearer than express it in any other way, because it tells you why we, in some cases, we have the factor 1/2, in some cases we don't. And let me remember the definition of signal-to-noise ratio. Average power divided average signal power divided by average noise power, and this is the product of two terms: EB over N0, energy per bit divided by power spectral density, and bandwidth efficiency, RB over W. So we can express RB over W given by the capacity versus EB over N0, and we see that the capacity formula divides this plane into two areas. On the left, we cannot have, on the left of the blue curve, over here, we cannot have reliable transmission, and all system will be centered in this area. It's common to distinguish between the bandwidth limited region and the power limited region. The bandwidth limited region is a region in which we want to achieve a high bandwidth efficiency, RB over W. This line corresponds to 2 bits per dimension pair. Remember that RB over W can also be expressed in bits per second per hertz or bit per dimension pair. And 2 bits per dimension pair correspond to 1 bit per dimension. So whenever our system forces us to use a transmission scheme with more than 1 bit per dimension, we are saying that we are in the bandwidth limited region, or vice versa. If our system is bandwidth limited, bandwidth is at a premium in our system, then we'd better work in this area. Otherwise, we are working in the power limited region. Power limited region is one in which our bandwidth efficiency is smaller than 1 bit per dimension. We need to save power. Consequently, we need to be as close as possible to this limit of minus 1.6 dB. Another possible representation, another possible graph that expresses how things go is expresses the so-called constellation constrained capacity. Constellation constrained capacity is the plot the capacity versus taking into account the constraint due to the signal constellation that we are using. The capacity achieving signal are Gaussian. So if we want to achieve capacity, in principle, we should transmit symbols that are Gaussianly distributed. In practice, we shall be forced to use signals that don't have a continuum of amplitude, but signals that are constrained to a finite signal constellation. That may be a 2 PSK, for example, 4 PSK, 8 PSK, or whatever. In which case, we observe that the capacity of a system using these elementary signals cannot exceed the amount of information that is carried by a single signal. Whatever we do by using 8 PSK, we would never be able to transmit more than 3 bits per dimension pair, simply because each signal carries a maximum of 3 bits of information. Okay? So we see that for small values of EB over N0, essentially all constellations are just as good as the capacity achieving constellation, the Gaussian constellation. As we move away from small values of EB over N0, then we'd better use a larger constellation if we want to achieve a constrained capacity that is close to the unconstrained capacity. Okay, so as we increase the size of the constellation, you see that the curve become closer and closer to the Gaussian signal constellation. Okay, that's about it for the Gaussian channel. Let me recall briefly what we have seen. First of all, a number of definitions essentially centered on the use of dimensions rather than hertz, etc., to define the parameters that are needed to evaluate the signal. Okay? Bit per dimension rather than the bit per second, etc., because these are useful definition. And for example, the capacity can be measured in bit per dimension. They have defined the bandwidth, the Shannon bandwidth, okay, and defined as a number of dimensions of the constellation divided by 2 times the duration of a single waveform. And this is the minimum bandwidth that we need for transmission. We have defined the efficiency of the use of the constellation in the sense that number of bits per dimension pair, and we use this in this formula, for example, RB over W, that can be defined only in terms of number of signal in the constellation and Shannon bandwidth require that. We have evaluated the error probability, and we have evaluated by simple approximation an expression for the bit error probability. So this is essentially summarizes thing that I assume you were familiar with. Now we shall see how this concept translates into a new set of expressions, a new set of formulas, when instead of considering the standard additive wide Gaussian noise channel, we are considering different channels. In particular, we shall focus on a fading channel, channel affected by flat fading, and tomorrow we'll see how this formula translates into a situation when we have multiple antenna transmission. So I can stop here for a 20-minute break, and then we'll resume with fading sound.
That's great, thank you.
I noticed that they are not in the right order, unfortunately. Not too bad, because this is section 4.
Right, I thought it was intentional. I saw this.